Welcome back, everyone. Today we're going deep, really deep, into the world of rotating black holes.
Rotating black holes as a source of energy, that is.
Exactly, as a source of energy.
Hmm.
Most people think of black holes as these cosmic vacuum cleaners just sucking up everything in sight, but
Yeah.
it turns out there's a lot more to the story.
There is, and it's pretty exciting stuff.
We're going to be looking at a fascinating academic paper that dives into
Yeah.
how these incredible objects can actually power some of the most energetic events in the universe.
Oh.
It's really mind-blowing.
And it's not just mind-blowing, it's efficient. It's unbelievably efficient.
Right, and we're talking efficiency levels that dwarf even nuclear fusion. I mean, that's
Right.
saying something. But before we get ahead of ourselves, let's start with the basics.
Sure.
A black hole, as you probably know, is a region of space-time
Yeah.
where gravity is so strong that nothing, not even light, can escape.
Exactly. And that point of no return is what we call the event horizon.
The event horizon, right?
Yeah.
Anything that crosses that boundary, that's it. Game over, gone forever.
It's gone.
But here's the thing. Not all black holes are created equal, are they?
No, they are not. There are actually four main types that we classify black holes into based on their mass, their charge, and their angular momentum.
Yeah.
And they are Schwarzschild, Kerr, Reisner-Nordstrom, and Kerr-Newman. But for our deep dive here, we're going to focus on the Kerr black holes.
Kerr black holes. Why Kerr black holes specifically?
Well, those are the ones that rotate.
Oh.
And they're really the most astrophysically relevant because most, if not all, black holes that we've observed, we think are spinning.
Because the stars that they're formed from, those are rotating as well, right?
Precisely.
It all makes sense. Okay, so we've got these spinning Kerr black holes. What else do we need to know about them?
Well, there's a fundamental concept called the no-hair theorem.
No hair theorem. Okay, that sounds intriguing.
And basically what this theorem states is that no matter what kind of matter went into forming a black hole, all the information about that matter, except for its mass, charge, and angular momentum, is lost.
So it doesn't matter what it was made of. It all gets boiled down to these three basic properties.
Exactly. To an outside observer, all you can really determine is its mass, its charge, and its spin. That's it.
Okay, so black holes are kind of like the ultimate simplifiers. They take all this complex stuff and reduce it down to these fundamental characteristics.
That's a great way to put it.
So now that we've got the basics down, how do we even start talking about extracting energy from a rotating black hole? I mean, where does the energy even come from?
It's all about space-time curvature. And this is where Einstein's theory of general relativity comes in. It tells us that gravity isn't really a force, but a consequence of this curvature of space-time caused by the presence of mass and energy.
So the black hole warps the fabric of space-time around it, and we experience that warping as gravity.
Got it. Yeah, exactly. But now, think about a Kerr black hole with its rotation.
Right, our spinning black hole.
It adds another layer to this whole idea of space-time curvature. It's not only warping space-time, it's dragging it along with its spin.
So it's not just a dent in the fabric, it's more like a swirling vortex.
Yeah, that's a perfect analogy.
Okay, I'm starting to get the picture. So this region around the black hole where space-time is being dragged along, what do we call that?
That's the ergosphere, and it's outside the event horizon, which is key.
Okay, so even if you were unfortunate enough to get caught in this ergosphere's swirling space-time, you could still escape, theoretically.
Yes, in theory you could, and it's this ability to escape from the ergosphere that makes energy extraction from a rotating black hole possible.
I see. So we're not talking about dipping into the event horizon and grabbing energy from within the black hole itself.
No, not at all.
It's all about manipulating the energy in this ergosphere region.
Oh, exactly.
Okay, that's helpful. But there must be some limits, right? I mean, how much energy can we actually extract from a rotating black hole?
Well, that's where Stephen Hawking's area theorem comes in. This theorem basically states that the surface area of a black hole's event horizon can never decrease. It can only stay the same or increase.
So as you extract energy from a rotating black hole, its rotation slows down, eventually becoming a Schwarzschild black hole, which has the maximum surface area for a given mass.
Precisely. And that sets a limit on the amount of energy we can extract. Calculations show that the maximum energy you can get from a Kerr black hole is 29% of its mass energy.
29%. That's an incredible amount of energy, especially when you compare it to something like nuclear fusion, which is only about 1% efficient.
Right.
It really highlights the incredible energy potential that these rotating black holes have. Okay, so we have this limit, 29%. But how do we actually extract this energy? What are the mechanisms involved?
Well, one intriguing idea proposed by Roger Penrose is called the Penrose process.
The Penrose process. Okay, I'm all ears. Tell me about this.
Imagine a particle entering the ergosphere. This particle splits in two, with one part falling into the black hole carrying, well, what we would call negative energy.
Negative energy, okay.
This effectively reduces the black hole's rotational energy. The other part escapes, carrying more energy than the original particle had.
So it's like we're tricking the black hole into giving us some of its spin energy.
You could say that, but the Penrose process is very delicate. It requires incredibly specific conditions that, frankly, are unlikely to occur naturally.
So while fascinating in theory, maybe not the most practical way to power our spaceships just yet.
Probably not. But there's another mechanism that might be more realistic and plays a crucial role in explaining some of the most energetic phenomena in the universe. We call it the Blandford-Znajek mechanism.
Okay, now we're talking the Blandford-Znajek mechanism. This sounds like it's getting to the heart of the matter. Tell me more.
So picture this. You have a rotating black hole surrounded by what we call an accretion disk. It's this swirling disk of gas and dust that's spiraling towards the black hole.
Right, the accretion disk. We've all seen the artist's impressions.
Now, this accretion disk is incredibly hot and ionized, meaning it's full of charged particles.
Okay.
And these charged particles are interacting with the black hole's magnetic field, a powerful rotating magnetic field.
Ah, so the black hole's spin is affecting its magnetic field as well.
Exactly. The rotation twists and amplifies the magnetic field lines, and these rotating field lines act like, well, a giant dynamo interacting with the charged particles in the accretion disk.
And it's this interaction that creates those incredible jets of plasma we see shooting out from the poles of some black holes, the ones that literally outshine entire galaxies.
Precisely. The Blandford-Znajek mechanism proposes that this interaction launches these jets outwards at nearly the speed of light, carrying away vast amounts of energy extracted from the black hole's rotation. And yes, those are the jets we see in active galactic nuclei, or AGN.
So we're seeing the black hole's spin energy converted into these powerful jets of energy. Amazing.
And the power involved is staggering. We're talking about energy levels that exceed the total energy consumption of the entire Earth by, well, it's an almost unimaginable factor.
Wow. Okay, we've gone from a theoretical limit on energy extraction to this mechanism that might be driving some of the most energetic events we see in the cosmos.
It's quite a leap, isn't it?
It is. So we've laid the groundwork for understanding rotating black holes as these incredible energy sources. But how does all of this play out in reality? Are things as simple as the models suggest? That's what I'm eager to unpack next.
Well, as with most things in astrophysics, the details can get a bit messy. The real-world picture is always more complicated.
It is, yeah.
So it's not as simple as just dropping a particle into a black hole's ergosphere and boom, out comes a burst of energy.
Uh-oh, if only it were that easy. Remember, the Penrose process needs some incredibly precise conditions that are, well, let's just say they're unlikely to occur naturally with that level of precision.
Right. And even the Blandford-Znajek mechanism, while definitely more plausible, it still involves all these incredibly complex interactions. You've got the black hole's magnetic field, the accretion disk, swirling plasma.
Yeah.
It's a lot.
Especially in such extreme gravitational environments, I can imagine those interactions would be incredibly difficult to even model, let alone observe directly.
Exactly. It's a real challenge. But astrophysicists, they're a persistent bunch.
I bet they are.
They're constantly working on their models and simulations, trying to bring in new data from observations, new theoretical insights, all to get a clearer picture of how these energy extraction mechanisms actually work in real black holes.
So it's this constant back and forth. Theory informs observation, observation informs theory, and so on.
Exactly. A constant dance. And that's where the excitement lies, really. The more we learn about real black holes, the more we refine our models, and the closer we get to truly understanding these incredible processes.
Okay, I'm following you. So what are some of the key questions that researchers are trying to answer through all these efforts? What are the big mysteries that still need to be solved?
Well, one of the most fundamental questions revolves around magnetic fields, specifically their role in the Blandford-Znajek mechanism. We know that magnetic fields are crucial for launching those powerful jets, for collimating them.
Right, keeping them focused.
Exactly. But the specifics, how these fields are generated, how they're sustained, how they interact with with the accretion disk and the black hole itself,
Right.
that's still very much an active area of research.
So it's like we've got this giant cosmic engine, but we're still trying to figure out the blueprints.
That's a great way to put it. And then there's the question of jet stability. These jets, they can extend for vast distances. I mean, we're talking millions of light years in some cases.
Millions of light years.
And yet they maintain this remarkably narrow focused beam.
It does seem counterintuitive. I mean, you've got
Yeah.
something so energetic, so powerful, and yet it maintains this focused structure over these mind-boggling distances.
It's a puzzle, definitely. And researchers are exploring a number of possibilities. The role of magnetic fields, of course, the dynamics of the accretion disk, even the influence of the black hole spin itself.
So it's this intricate interplay of factors that all come together.
It seems that way.
It's amazing to think that by studying these jets, these byproducts of the energy extraction process, we can learn so much about what's happening near the black hole itself.
Oh, absolutely. These jets, they're like cosmic messengers, you know? They carry information about the processes that are occurring deep within the accretion disk, close to the event horizon. We can analyze their properties, their composition, their speed, their energy output. All of that tells us something about what's happening in those extreme environments.
It's like cosmic archaeology, using the light from these jets to dig into the past and understand the events that led to their creation.
A very poetic way to put it. And it's not just about observation, of course. Theoretical astrophysicists are hard at work, too, creating more sophisticated models, incorporating the latest observational data, and running simulations, trying to see what matches reality.
It's that constant interplay between theory and observation that really drives science forward. And speaking of pushing forward, we touched on the idea of advanced civilizations potentially harnessing energy from black holes. Is that something that's seriously considered in the scientific community, or is it more science fiction?
It definitely sparks a lot of, well, let's say what ifs. It's a fascinating thought experiment, but in terms of hard science, there's no evidence to suggest that any civilization, no matter how advanced, has actually achieved the kind of technological prowess you would need to harness black hole energy.
Right, right. But it's still fun to think about.
It is. I mean, the idea that something as seemingly destructive as a black hole could be a source of clean, virtually limitless energy, it's both intriguing and a little bit daunting.
It really challenges our preconceived notions about energy, about technology, about what's possible. But for now, it seems like it's firmly in the realm of speculation.
For now, yes.
But, even exploring these what-ifs, it can lead to new insights, inspire further research. It reminds us that the pursuit of knowledge is a journey. And what seems impossible today, well, tomorrow, who knows?
Exactly. The universe is full of surprises, and our understanding of it is constantly evolving.
Okay, so we've covered a lot in this deep dive so far. We've gone from black holes 101, their structure,
Yeah.
to exploring these mind-boggling mechanisms for energy extraction. We've talked about the challenges of observing and modeling all of this, and even ventured into the realm of advanced civilizations and their potential black hole power technologies.
It's been quite a journey.
It has. But before we wrap up, I want to shift gears a bit, touch on a more philosophical question. We've been discussing black holes as energy sources, but what about the flip side? Can we actually create or even manipulate black holes ourselves?
Now that's where we really do enter the realm of science fiction,
Oh,
at least for the foreseeable future. I mean, the theoretical possibility of creating or manipulating black holes, sure, it's intriguing.
yeah.
But the technological hurdles, the energy scales involved, it's almost beyond comprehension. It dwarfs anything we can even imagine doing right now.
So no black hole power plants anytime soon.
Let's just say it's not exactly on the top of our priority list.
Fair enough. So while black hole engineering may be a distant dream, the study of natural black holes, their energy extraction mechanisms, that continues to be an incredibly valuable and frankly, mind-blowing area of research.
It is, and who knows, maybe one day our understanding of physics will have advanced to a point where we can at least start to contemplate such possibilities.
Okay, so we've covered a lot of ground in this deep dive. We've gone from the basic concepts of black holes and their structure to exploring the mechanisms that could allow us to extract energy from them.
Right.
We've discussed the challenges of observing and modeling these processes in real astrophysical objects.
Yeah.
And we even ventured into the realm of speculation about advanced civilizations harnessing this cosmic power. But before we get too lost in the philosophical implications, let's bring it back to the core takeaways from our deep dive today.
Yeah.
What are the key points you want our listeners to walk away with?
Well, I think the most crucial points are, first, rotating black holes aren't just cosmic vacuum cleaners, they're incredibly efficient energy sources.
Mhm.
Second, the Blandford's-Najek mechanism offers a compelling explanation for how this energy extraction might actually occur in real astrophysical objects, powering some of the most luminous phenomena in the universe. And third, while actually harnessing black hole energy, that remains a distant prospect. The study of these objects is, well, inspiring new discoveries, and it's expanding our understanding of the universe's most extreme environments.
Those are fantastic points. And
Yeah.
to build on that, let's break down each of these takeaways a little bit further, starting with the first one. Rotating black holes as energy sources. What makes them so unique in this regard?
Oh, it really comes down to their structure, I guess, and the extreme physics that happen around them. You know, you combine immense mass and rapid rotation and powerful magnetic fields. It creates this environment where energy can be extracted in ways that we just don't see anywhere else, not with other celestial objects anyway.
It's that unique combination that really sets them apart. We talked about the ergosphere, that region where space-time itself is being dragged along by the black hole's spin.
Right.
And we discussed how that enables processes like the Penrose process, where particles can theoretically gain energy from interacting with a black hole's rotation.
Yeah, and while the Penrose process is definitely fascinating from a theoretical standpoint, it's the Blandford's-Najek mechanism that seems to be the real powerhouse, the one that's really driving those energetic phenomena that we observe.
So just to recap for our listeners, the Blandford's-Nash mechanism describes how that interaction between the rotating black hole's magnetic field and those charged particles in the surrounding accretion disk
Right.
that can launch these incredibly powerful jets of plasma.
Yeah.
And those jets are what we see as the brilliant emissions from active galactic nuclei, or AGNs.
Precisely. The Blandford's nudge mechanism, it's really the best explanation we have right now for how these AGNs can outshine entire galaxies, releasing energy on scales that are, well, they dwarf anything we can even comprehend here on Earth.
It is mind-boggling. But as with any scientific model, I'm sure there are still some gaps in our understanding. What are some of the big unanswered questions, the ones that researchers are still grappling with when it comes to the Blandford's-Nash mechanism and I guess black hole energy extraction in general?
Well, one of the key challenges is accurately measuring the properties of black holes, especially their spin. You see the efficiency of the Blandford's Najek mechanism, it's directly related to how fast the black hole is rotating. The faster the spin, the more energy that can be extracted.
So knowing the spin of a black hole is crucial for understanding just how much energy it can potentially release.
Yeah.
But how do we even measure the spin of something like a black hole? Something that's so elusive, so compact.
It's tricky. We have to rely on indirect methods. One way is to observe the orbits of stars and gas clouds that are close enough to the black hole to be influenced by its gravity, and by analyzing their orbital motions, we can infer the black hole's mass and its spin.
So we're using the movements of these celestial objects as tracers to map out this invisible gravitational field of the black hole.
That's a good way to put it. Another method is to study the X-rays that are emitted from the hot swirling gas in the accretion disk. And these X-ray emissions, they can actually carry signatures of the black hole's spin,
Yes.
allowing us to estimate its rotation rate.
So it's a combination of careful observation and really sophisticated modeling that gives us these insights into black hole properties. And I imagine as our observational techniques improve, as our measurements become more and more precise, our understanding of these processes is only going to get more refined.
Absolutely. And it's not just about measuring the spin. There's a lot we still don't know about the finer points of the Blandford's-Najek mechanism itself.
Like what are some of the biggest mysteries that still surround this mechanism?
Well, one of the key areas of ongoing research is the role of magnetic fields. We know that they're absolutely crucial for launching and collimating the jets, but the details of how those fields are generated, how they interact with the black hole, with the accretion disk, that's still very much being investigated.
It's like we're trying to understand this complex electrical circuit, but we can only see the sparks, the flashes. not the wiring itself.
That's a great analogy. We're still working on putting together the complete picture of how the magnetic fields are generated, how they're sustained, how they're shaped by the black hole's rotation, by the dynamics of the accretion disk. It's complicated.
And then there's that question of jet stability, right?
Yeah.
How do these jets maintain such narrow focused beams over such incredibly vast distances, sometimes stretching for millions of light years?
Yeah, that's another major puzzle that we're still trying to solve. We're exploring a number of factors that might contribute to that stability. It could be magnetic confinement or the influence of the black hole's spin, maybe even interactions with the surrounding intergalactic medium. It's probably a combination of a lot of different things.
So it's a multifaceted problem.
Very much so.
But with a lot of active research going on to try and solve it, it's it's incredible to think that these jets, these byproducts of the energy extraction process, they can carry information about the extreme physics that's happening near the black hole over such vast cosmic distances.
They really are. They're like cosmic messengers, giving us this glimpse into environments that would be impossible to observe directly otherwise.
Well, this has been an incredible deep dive into the world of rotating black holes as energy sources. We've gone from the basic concepts to the mind-boggling mechanisms at play, and we even touched on the tantalizing possibility of one day harnessing this cosmic power ourselves.
It's a testament to human curiosity, really, and
Yeah.
to the ingenuity of scientists that we can even contemplate these sorts of ideas.
And even though we still have so much to learn, the journey of discovery is just as rewarding as the answers themselves, I think.
Oh, absolutely. The pursuit of knowledge is an ongoing adventure, and every new insight, it brings us closer to understanding the universe and our place in it.
So to wrap things up, what's the one key message you want our listeners to take away from this deep dive?
I think the most important message is that rotating black holes, these objects that we once saw as cosmic abysses, as just engines of destruction, we now recognize them as some of the most powerful energy sources in the universe. And their study, it hasn't just revolutionized our understanding of gravity and the nature of space-time. It's opened our minds to possibilities that we couldn't have even imagined before.
That's a great reminder that the universe is full of wonders, and that our exploration, it's really just begun. And who knows what incredible discoveries await us as we continue to probe the depths of space and unravel the mysteries of these fascinating objects.
The future of astrophysics is very bright, and I'm excited to see what new insights, what new breakthroughs lie ahead.
Thank you so much for sharing your expertise with us today. It's been a truly enlightening conversation. And to our listeners, thank you for joining us on this incredible deep dive into the world of rotating black holes. Keep exploring, keep questioning, and never stop marveling at the wonders of the universe.